Welcome to the 29th lecture video for Physics 4A. We wrap up fluid mechanics and all topics coverage of this semester with this lecture set. The first segment wraps up what we started in the last lecture set, fluid statics, mainly analyzing arrangements of forces that are set up with the fluids at rest. Here, by looking at an application of hydraulics that result in a mechanical advantage. And we start and finish our brief coverage of fluid dynamics in discussing the continuity equation, which expresses a kind of conservation of flow, and by looking at the textbook's derivation of Bernoulli's principle, a statement of conservation of mechanical energy in moving fluids. This lecture wraps up all the topics we will cover this semester. We do have one review lecture set in which we will do a recap and review of topics we have covered this semester, but not so much of the problem-solving techniques. So I guess I can kind of break it up into three different parts. One is something called Pascal's principle. And do you guys remember simple motion that I have mentioned from time to time in this class, I hope? Simple motion, does that phrase mean anything to people? Yes? Ratana, what does a simple motion mean? Or do you remember any example of simple motion? Pulley. Pulley can be an example of simple motion, although, so what does a pulley do that you would call it simple motion? So if I'm using a pulley as a way to build a simple motion, it would look like this. I would have pulley here, and actually I would have a string that's attached like this. And just so that I can pull it downward, I might have an additional pulley here. I mean, it's not necessary, but I might. It makes things easier. And then this would go around, and I would be applying downward tension here. And I would attach a mass to this first pulley here, and this is an arrangement that someone might call simple motion. What does this device do? Let me ask you this question this way. Let's say you want to apply just enough tension so that this thing doesn't fall. How much tension should I apply? Do I need to apply mg? Or do I need to apply something else? Isha? It's less than mg. Here's the quick way to kind of get at it without doing a bunch of math. So you have tension here. Hopefully you have this intuition that the tension you need to, this is tension, same tension here. And it's the same string, no friction or whatever. So this is also the same tension. So on this pulley are two upward tensions of the same amount T here, which is going to equal the weight of this thing. So that means my tension must be half of mg. So this is an example of simple motion. Did we never go over this in class? Might have been in one of the sample exams maybe, and some of your homework possibly. Well, I should have brought this up earlier. So what do you think the purpose of a simple motion is? Like, what does it accomplish that makes it kind of an arrangement that you would want to make for doing something useful? Steven? Yeah, you can lift more weight by applying less force than what the entire weight of that is. And do you remember any other arrangement that accomplishes something like this? You have seen maybe one more example that's perhaps familiar.
I guess we haven't explicitly brought it up as an application of this. It came up in rotation, or it could have come up in rotation, or you would have seen something like this in rotation. So this is why this is here. Let's say I have something super heavy, actually heavy. And let's say I want to lift this. You know, the way this is, I would have to apply a force of about 2 kilograms to directly lift it. But if I set up a very particular arrangement, I can lift it, not like entirely, but you know, get it to move by applying a force that's less than 2 kilograms. The way I would do it is I have this pivot point, I stick something underneath, and I kind of have to do it so that it doesn't slide out. and so this pivot, you know, something is holding this in place so that it's not moving. I have to take this end and do it like this. Then amount of force I have to apply at this end is way less than 2 kilograms. Like, do you remember seeing something like this before? Do you remember using something like this before? Right?
You use it, those are the jacks that you use to lift the car.
So jacks, they use something different. So I actually have a jack here. This is a jack, right? Jack uses something different. It uses this screw thread that works kind of like a ramp does. So but this is actually another example of simple machine, because the only thing that's operating it is your hand turning this, but this can lift a fair amount of weight. By turning this, I can lift. I guess I haven't actually tried it with this jack, but you know, I guess depending on car jack, you might have a lever thing that you move up and down, right? Yeah. So I guess so at this point, I shouldn't waste too much time bringing up all the examples of simple machine. All these simple machines have really two common features. One of them is what's called a force multiplier, and that's what you have seen here. So all the simple machines, you can describe them by something you would call force multiplier. This is the entire point of simple machine. Like, why do you want to arrange pulleys this way? So that you can lift a weight that's heavier than what you can lift with the bare hands alone. Why do you want to use a lever? Or I guess a crowbar is another example of lever. It's so that you can move this object by applying a force that's a lot less. I think Archimedes is actually the one who said, is it Archimedes? Some Greek guy said, give me a place to stand and a lever and I can like move the earth. Does that phrase sound familiar? No? Never mind, we don't care. So you know, in all those cases, the main purpose is the force multiplier. You apply a smaller force to get a larger output force. But there's always a price to pay. I mean, you know, if you could get this force multiplier without anything else, anything that you pay in return, you would have like 100 of these pulleys, and that'll make you feel like a Superman. You can, you know, lift 100 times the weight that you can normally lift. But there's something you have to pay, which is why there's a limit to where this is useful. So there's a quantity that you can, in all this simple machine arrangement, you can always say you might be multiplying force, but you are not multiplying this. This quantity remains the same. What quantity here, if you were to calculate, would remain the same? What one thing have you learned in this class that you cannot get for free? Yeah, energy. So as you are using this simple machine arrangement, energy is going to be conserved. So however much work you put in here, the amount of work you get here will be the same. Meaning, so you were able to apply double the amount of force at this end than what you're applying. If you analyze this carefully, you will see that for every meter this can go up, I have to pull down 2 meters of string, so that the force times distance is always going to be the same. It's the same deal here. With the lever, you look at how much this end is moving. So because of the geometric arrangement here, for like a 10 centimeter, oops, for something like a 10 centimeter, this far end moves. This end only moves like a centimeter. So if I'm multiplying my force by a factor of 10, then my distance goes down by a factor of 10, so that the amount of work you get out at this end is the same as the amount of work you put in here. And it's the kind of same thing with the jack, same thing with the ramps, same thing with any kind of simple machine arrangement that you would have seen. And the reason I'm bringing up all of this is this fluid actually gives you one more arrangement where you can get simple machine. It's so this idea of simple machine, it's kind of it's a general idea. There are many different arrangements you can utilize to get something that has a force multiplier and same work in as work out. And the arrangement with the fluids gives you one more arrangement where you can have this simple machine. You multiply force, but you have still the amount of work you get out is the same. Question?
No, I was going to mention hydroelectricity would be an example of a single machine.
Hydroelectricity is power generation. So you are thinking of like electric dams and that kind of stuff, right?
Or the one with the wheels that capture the water.
Yeah. So that's more of electricity and magnetism. I mean, energy is coming from the gravitational potential energy of water that's going into turning the generator. But there we actually have to talk about electromagnetic induction, which is topic of physics 4B, not this class. But so let me write down the name for it because some people might have heard of it. So this arrangement of simple machine, we call this hydraulics. And actually, it's part of a working part of a lot of different real-life machines. So I may be misspelling it, hydraulics. So like if you are looking at any heavy machinery, it probably has some kind of hydraulics in there that helps people multiply force so that it's like, you can use this instead of gear maybe. And old-fashioned power steering used also some kind of hydraulic power steering. I think these days power steering in the car is more of electric power steering, but old car like mine has hydraulic power steering. And so let me describe just the basic idea behind the hydraulics. And this is the kind of setup. Let's use car as an example. So let's say you have a platform that has, I don't know, 2,000 kilogram car sitting on it. So it'll be something simple like a tiny sedan that's only 2,000 kilograms heavy, 2,000 kilograms. And I want to say, well, there's some arrangement we can make where force that's applied by a single person, let's say you have a guy who weighs, let's say he weighs 100 kilograms. A guy who weighs 100 kilograms can lift this car. You might wonder how, and that's the arrangement that you can make with the hydraulics. Let me describe the sort of the fluid arrangement that you would have, so that this 100 kilogram person, using his weight alone, can actually lift this 2,000 kilogram car. This is the arrangement. You have this person standing on some kind of platform. Let's say let's attach it to something here. I'm just gonna, this is my representation of some standing platform. And this is already on a platform that's going to be attached here. And these two platforms are connected by a pipe that contains a fluid. So they're connected by an enclosed system that contains fluid. And so let's see, let me draw it this way. So this is the pipe, the left-hand pipe of a smaller diameter that's going to be connected to, on the right side, to a pipe of larger diameter. Good? And I guess it has to be full, for this to work, it's called hydraulics because it's probably going to be filled with water. It needs to be filled with what people would call incompressible fluid. A kind of fluid where if you apply significant amount of pressure, the volume doesn't change much. And that actually describes most liquids you know. So this just cannot be air. If it's air, then it would just compress and not do what we want it to do. And I'm going to claim that with this arrangement, you can have a 100-kilogram person standing on a platform that's going to somehow apply enough amount of force that's going to cause this car to rise. Okay? And let me try to describe the situation. And along the way, I'm going to describe a principle known as Pascal's principle. But I think without actually naming the principle, it's something that will make intuitive sense to a lot of people. So let's imagine you have, before this person is standing here, what would you say the pressure of the liquid in this spot is? What would you say the pressure is before there's a person standing here? Like, what is the pressure of water here? Is the water here at any kind of pressure? What kind of pressure? So like water here, is that under any kind of pressure?
The air pressure.
It's under air pressure. So it's at atmospheric pressure. So I could say this point, initially, the initial pressure would be my atmospheric pressure, right? And in fact, could you say that for most of this, now, as you go lower, it'll be at higher pressure. But as you go back up to surface here, can you say that this is also at atmospheric pressure? Yes? Right? Okay, so that's our starting point. So I guess you also have to imagine there's no car here. Yeah? And this is what I want you to picture. So suppose I've placed a person on here, then there will now be additional pressure here due to the weight of the person, right? So pressure after, the pressure, so at this same spot, pressure after the person gets on is going to be my initial pressure, the atmospheric pressure, plus the pressure due to this person. Okay? One way to express that would be, if I know the cross-sectional area here, let me call that A1, then the pressure due to the person would be whatever force this person is applying, call that F1. F1 divided by area 1. Right? That's how much pressure this person is exerting by standing here. Okay? And this is what I want you to think through. If the pressure in this part of the liquid is increasing, what do you think might be going on with the pressure in this other part? Can this remain at the same pressure it was at before? Can this remain at simply the atmospheric pressure? Or will it have to change to something else? Change. Why? Yeah, because of the external pressure. Actually, I guess this is how I want you to imagine. You can think of this iteratively. Let's say as the man stands on here, that exerts additional pressure here. And let's say for the time being, that's the only change that happens here. Nothing else changes. Then next to pass around, this is what you're considering. Imagine this fluid element. These fluid elements, pressure on one side of them is greater than the pressure on the other side. So this element is going to get pushed. And the one next to it will get pushed, get pushed, get pushed, get pushed, until that change in pressure kind of propagates through the entire fluid. And at this end, you will end up with the same change in pressure. The pressure at this end of the fluid will be the atmospheric pressure plus this same additional pressure that was applied here. So F1 over A1. Okay? This is what's known as Pascal's principle, that in a static fluid, any change in pressure in one part of the liquid gets transmitted throughout the liquid. It's because liquid can flow. If there's a pressure difference from one end to the other that's at the same height, then that pressure difference will cause the fluid to flow until the pressure equilibrizes. Well, it becomes equal throughout the entire thing at the same height. Okay? Now, this is what I want you to look at. You have this additional pressure. Now, what is the additional force on this platform due to additional pressure? Is it simply F1, or is it going to be something different? So, you have pressure. What do you need to do to get to the force? To get to the force on this platform? Multiply by area, right? So is it this area that we are multiplying? No, it's the area of this surface that we are multiplying by. So to get this force F2, you multiply by the larger area here. So F2 here, F2 is equal to this additional pressure, F1 over A1 times A2. So here the force multiplier is the ratio of these two areas, A2 over A1 times F1. So here, with the car being 20 times heavier, you would want this area to be 20 times the area of this. Then the weight of the 100 kilogram man is enough to lift the entire weight of this 2,000 kilogram car. So this is another simple machine. You have a force multiplier that's given by this ratio of the areas because of the way pressure works. So I guess here the challenge would be, this is why I mentioned the limitation of simple machine. A simple machine like this arrangement, which has no motor, no sort of external source of energy, whatever energy this car gains must come from energy loss of this 100 kilogram man. Can you see that amount of work done on the car will be equal to the amount of work that the man is doing? Or I guess the easiest way to talk about it is in terms of potential energy. So however much potential energy this gains is equal to how much potential energy the man is losing. Arjun, can you explain how that makes sense? Like, how does that happen? Okay, so you are somehow arguing change in height of the car is less than the change in height of the man. How? What aspect of fluid would you bring up to say, because of this, change in height of the car must be less than the change in height of the man, probably by a factor of 20. Stephen?
The displacement of the water.
Yeah, displacement of water. So whatever volume is gained here must be the volume that's pushed out here. Their cross-sectional areas are different, but their volume must be, so volume must be the cross-sectional area times the height. So this area 1 times height 1 must be equal to area 2 times height 2. So the sort of the reciprocal of the ratio of these areas is the ratios of the height. So if the area is 20 times much greater here, then the height change is 20 times less. So this is another arrangement of simple motion that conserves energy. There's no external source of power. The only thing it does is it multiplies force, but it does it at the cost of reducing the displacement, which means amount of work done is the same. So this is one useful thing, and if you wanna give it a name, it's really the biggest application of what some books call Pascal's principle. So there's really two ideas I want to talk about that has to do with the fluid in motion. It's something called the continuity equation and Bernoulli's principle that I'll try to give you some intuition for, because especially continuity equation, it sounds fancy, but it actually describes a really simple idea that you kind of knew already. You just maybe didn't know the implication of. But let me start out with a little bit of demo. You might have seen this. This is a kind of popular demo dealing with the Bernoulli's principle. So I have this, flat, bendy piece of paper, and what I'm telling you now is I can make this paper bend up without touching it. And you might say, all right, the way you can do it is I can blow into it. All right, so that's one way to do it. But what I'm going to do is I'm going to make it bend up by blowing over it, blowing air over it. So when I do this, this comes up. And this is a result of something called the Bernoulli's principle that says when you have a fluid that's moving at some velocity, there's a related difference in pressure that occurs. So as I pass fluid here, that lowers the pressure in this region. Pressure here is higher, so that difference in pressure pushes the paper up. So this is a demo that you might, if you ever visit, exploratorium as a, not kindergartner, as a child, you might have seen it. If you didn't, all right, now you saw it. I want to get more mathematical, that you might not have seen in other science class. So the first thing I want to address is a consequence of something called continuity equation. Continuity equation, and there are well, at least two different ways of expressing this that I know of. One involves a differential calculus. I'm not going to use that. The other one looks more like an algebraic relationship, and I am going to use that. And this is really expressing a very simple principle that you'd figure out as you think through this demo. So this shows a flow of some kind of fluid here. That's what the simulation is simulating. And it has some adjustable parameters. I can adjust the flow rate, have less water flowing. I want you to pay attention to the unit. It's liters per second. So it's measuring how much volume of water is flowing per amount of time. So I can change the flow rate. Let me set it back to 5,000. That's the default. I liked it enough. Don't need anything else. And I can put sensors all over the place to measure what's called fluid speed. So this is, or fluid velocity. This is, regular kind of velocity. It's measuring, given this particle, how fast is it actually moving? It's moving at 1.6 meters per second. And the simulation is set up so that the speed at which this is moving does relate to the speed. So if I increase the flow rate, then one of the ways to do it is just have the particles moving faster, and speed is greater. Good? All of this makes sense? And I guess there's a pressure here, but we'll talk about that in a little bit. We don't need to talk about it right now. So this is the prediction I want you to make. I'm back down to a flow rate of 5,000 liters per second. And I'm going to make two changes here. I'm going to make this part of the pipe narrower. I'm going to make this narrower. And I'm going to make this portion of the pipe wider. How do you think the fluid speed as would be measured by placing this here or here? How do you think that'll change as I make these two changes to the pipe? As I make one section narrower, how do you think the fluid velocity should change? Wait, I heard increase. Did you say faster, Abdi?
Yeah, the narrower the speed is fast.
Okay.
And
Oh,
the wider
well.
is slow.
Anyone say a different answer? Same speed, okay. So, well, let's try it and see. I'm going to make this narrower. Let's see, this much up. Don't know. Yeah, you can kind of see with the particles that it's faster. So good job. You guys had the correct answer. A lot of people I would have assumed intuitively would answer that it slows down. At least for me, that would have been my answer. Like I would be thinking of like analogy to a traffic. Like if you have a narrower portion of the road, traffic usually slows down. The cars don't suddenly start going faster in the narrower portion. So Abdi, can you explain why you predicted that the fluid would be faster here?
Because the cross-section area of the volume is becoming narrower.
Okay, area is narrower. That's part of this being narrower.
And the pressure coming from that area is higher when they got that one. Pressure-
Oh, I see.
yeah.
I think this is maybe what you're thinking of, which is a good intuition to have. Like if you have a water hose and you want the water to be coming out of the hose faster, then what you do is you narrow the end of the thing, then the water comes out faster out of the hose, right? That's what you're thinking of. And by kind of blocking it off, pressure builds up here, so it makes it go faster. Yeah, all of that is consistent, but I want to actually look at it from a different perspective. So all of what Abdi was saying is correct. That when I do this, in fact, since I have simulation, let's see it. So let me bring this back to what it was. And I can actually put this pressure meter here to measure the pressure here. All right, it says some pressure, 120 something kilopascal. And you will see that as I make this narrower, wait, it doesn't increase. Something else must have happened. Oh, pressure here decreased. Is that right? I guess that's kind of right. And actually, we'll talk about this with the Bernoulli's equation. So one thing that is correct is there's a difference in pressure. So right now, the pressure between here and here is more or less the same. It's more or less the same pressure. But when I made this part narrower and made particles move faster, then that somehow decreased the pressure way here. So, all right, we'll look at that later. So for now, I want to come up with an explanation that doesn't have anything to do with the pressure, because what's happening with the pressure is a little bit weird. How would you explain why the particle is coming in relatively slow? It speeds up here. And here's a funny thing. Does it look like they're slowing back down here? Yeah, in fact, let me do this second part. Let me make this portion of the pipe wider. And let's see if they slow down further. Yeah, I make the pipe wider. And you can see that the water actually slows down more. And once again, that's counterintuitive. You think, in a traffic, when your road widens up, you speed up, you don't slow down. So what's going on here? Why does water speed up in the narrower portion and slow down in the bigger, wider portion? Once again, I don't want to really deal with the pressure, because what was happening with the pressure was weird. I don't want to have to explain that portion. Because this is what you'll see. In this wider portion, pressure increased. So, pressure starts out from 120 something, decreases, and then as you go out here, pressure increases again. So, something's going on with the pressure, and we'll talk about that with the Bernoulli's equation, Bernoulli's principle, but it's going to take some more work, so we will come back to that in a bit. How would you explain it without referring to pressure, Akti?
Because of the volume.
Okay.
From like the smaller, when you come out too big, you have to fill it that big.
You have to fill it that big. Okay. What do you mean by volume? Volume of what?
Volume of the pipe. When
Volume of
when
the.
it's becoming bigger, and the cross section.
Okay. That's closer.
Takes time to go through.
I do want us to focus on volume, but it's not the volume of the pipe that I'm concerned with, although that's part of the picture. The volume that I'm really concerned with is the volume of the fluid. And that's really that's the principle behind whenever somebody refers to something called the continuity equation. You see it in fluids. You see it when you deal with electricity and magnetism, upper division level. This, what's expressed in continuity equation always is the idea of conservation. It could be conservation, in this case, it'll be conservation of volume, because the kind of fluid we have here is an incompressible fluid. So here, it's conservation of volume. But if we're dealing with like a gas, something that can be compressed, then we might be talking of conservation of mass. Or in terms of electricity, which you might deal with in upper division electrodynamics, that's a conservation of charge. But in all these examples, the idea here, the important idea here is that there is some kind of a conserved physical quantity, like a physical object that's conserved. Once it exists in some place, it cannot simply disappear. It has to move through space. So here, one big hint here is that through all these changes in the pipe diameter and changes in the fluid speed, one thing actually remains constant. That's this flow rate. Let me show you with the measurement. I have one thing that actually measures flow rate. Where was it? Flux meter. This is what measures the flow rate. So flow rate starting here from here, that's the specified 5,000 liters per second. As I go to different parts of the pipe, you will see the, well, I'm not going to pay attention to flux. The only thing I'm going to pay attention to is the flow rate. Flow rate remains the same. 5,000 liters per second comes in through this section here. 5,000 liters per second has to go through this section because there's no space in between where they can accumulate. And as they go through, as they come to wider portion here, still 5,000 liters per second has to flow. So this is a place where it's nice to have an expression for flow rate, as in how does this flow rate of some volume per second relate to maybe the fluid speed. That'll help me explain why fluid is flowing faster here and in a way that keeps the flow rate constant. Okay? So I don't want to spend too much time on this argument, so I will just give you the answer. It's yeah, because this type of stuff is something that we would spend more time with thermodynamics and physics 4B. But for this class, we are just talking about something like this, so I don't want to spend too much time. So this is the sort of standard way to think about this. I'm thinking of flow rate. So I'm thinking of how much volume of water will cross over some space. So one way to express that is so this is the boundary I'm thinking of. So I'm looking at, okay, how much volume will cross over this? Well, let's just extend it out a little bit. Maybe it's about this much volume. that'll cross over this boundary in the next time interval. Good? So when I'm looking at this, there are two quantities for me to worry about. Here, what is the amount of volume? Well, that seems, so I guess what I would do is I would take the area and multiply by this distance, delta x. That would be my volume, right? Okay, so let me express the volume that way. Area times delta x. And then it's a question of in how much time is this whole volume going to cross over? So I'm looking at the duration of time of, let's say, delta t. Okay? That's the how much time it would take for the last of the particles here to finally cross over. So I can write down my flow rate this way. So flow rate would be volume per time, right? That's flow rate. So flow rate is equal to volume, area times delta x per time, delta t. Do you see some of these terms here being combined in a slightly different way that would give different physical meaning to some of these quantities? Asia. I have this delta x over delta t, right? So the meaning I can assign there is that for a particle here, it's crossing this distance delta x in time delta t. So these particles must be moving at some speed given by delta x over delta t. So that's my fluid velocity. So I can call this, well, this is my fluid velocity, v. So this is the expression we get for flow rate. Flow rate is equal to area times the fluid velocity. And you will see that, if you write down the units, all of that works out. And so in this particular context, this is what we would say based on the continuity principle, that my volume is conserved, meaning my flow rate across all these different cross sections has to remain constant. If it doesn't, then I have this weird situation where more liquid flows in than leaves, or more liquid leaves than flows in, and that just doesn't happen with the liquids because they cannot accumulate. So because my flow rate is the same throughout the entire pipe, I can write down something that looks like a conservation law equation. I would write it down this way. I'm going to imagine writing down my flow rate, let's say at a particular point along the pipe. And write down your flow rate at some different point along the pipe. And because the flow rate is the same here as here, I would have to say area 1 times fluid velocity 1 is equal to area 2 times fluid velocity 2. And let's say my area 2 is greater than area 1. So let's say I'm looking at the fluid velocity in V1. If you solve this for V1, this is what you get. V1 is A2 over A1 times V2. So this is a number bigger than 1. So the velocity in the narrower section is greater by the ratio of the areas. So this is one of the conditions that has to be enforced when you have a liquid like water flowing through a pipe. This is called the continuity equation, and that it's a starting point to start talking about some of the equations and expressions that fluid in motion has to obey. And this is one of the kind of simplest one because it's based on the idea of conservation of matter, really. It's based on conservation of matter. And now, we have to think about, okay, so if velocity increases, how is it increasing? Because increasing velocity, that actually relates to increasing kinetic energy. So the kinetic energy of these particles here is lower than the kinetic energy of the particles here. So something must be set up externally. Something must be set up in a way that energy is still conserved. So that's the next set of things for us to worry about. But at least this is a starting point. We can say that because the volume has to be conserved, no matter what else happens, at least this has to be true. Yeah? All right. So that's a continuity equation.
So this is the second attempt or another attempt at lecture material that does the proper derivation of Bernoulli's principle. I've done this in the past, and I gotta tell you that. So you will see it if you watch this lecture video. Every time I do this, I kind of mess it up. Every semester I make some subtle mistakes, and I got through this somehow, and with I mean, I'm okay with the edited version of it that's here. It doesn't have any serious mistakes in it at the end. But I gotta tell you that this length of it, it's highly unsatisfactory to me. It shouldn't really take 40 minutes. So let me give a second try at this lecture using the textbook resources. So instead of trying to drive this from scratch, which I've done here, and I can try to redo the exact same thing. But instead of that, let me read it through the textbook and as a kind of model of how I think you should be benefiting from this condensed written material that's available as your required course resource. So this is from chapter 14, which, if you recall, earlier we skipped. After chapter 13, we went straight to chapter 15 because we of all the 17 chapters that are in this long textbook, the one chapter that I thought if we rushed through it and we didn't spend a lot of time on, the one chapter we would be okay doing that is chapter 14. Because if you, the kind of the field you go into, maybe mechanical engineering or civil engineering, where fluid mechanics is important to you, you will learn so much more than what we can cover here. So it's okay to skim through it, rush through it. So within chapter 14, section 14.6, Bernoulli's equation, is where Bernoulli's equation is introduced and derived. So we'll read through this together, and I will pause and comment where I see something. And I gotta tell you, I haven't actually read through this in detail before. Maybe I should have, but one benefit is you'll get genuine modeling of what it looks like when someone's reading through a dense technical material like a physics textbook. I do have some benefit of knowing some of this stuff already, but I'll try to role play someone who's just seeing this for the first time. So section 14.6, Bernoulli's equation. So it says, as we showed in this figure, I have a feeling it's a figure in previous section, so let me right click and open a new tab so that I don't lose my place here. Yeah, it's in previous section. Yeah, okay. I think I'm okay with that preview over there. Yeah, so something narrowing and velocity changing. Yeah, good. I think they probably covered what we call continuity equation. The speed of the flowing fluid increasing, that's dictated by properties of fluid and geometric constraints on it. So when a fluid flows into a narrow channel, its speed increases. That means its kinetic energy also increases. The increased kinetic energy comes from the network done on the fluid to push it into the channel, right? The work kinetic energy theorem that we covered way back when we were introducing energy. Also, if the fluid changes vertical position, work is done on the fluid by the gravitational force. So there must be some kind of potential energy associated with that. So as I'm reading it, I'm connecting it to the things that I've learned previously. You've heard me say physics is cumulative. This is how it's cumulative. Um, a pressure difference occurs when the channel narrows. This pressure difference, this is I think, basically a statement of experimental fact, and hopefully we'll see some derivation that justifies theoretically why this should happen. This pressure difference results in a net force on the fluid because the pressure times the area equals the force, okay? And this net force does work. I think that makes sense conceptually. Recall the work energy theorem. Yeah, what I was saying earlier. Difference in the kinetic energy comes from the net work done. The net work done increases the fluid's kinetic energy. As a result, the pressure drops in a rapidly moving fluid, whether or not the fluid is confined to a tube. Okay, that's interesting. Um, I don't know if that makes full sense, but I'll move on. So when you are reading a dense technical material, what I would say is you have to strike a balance. So you can't speed read through it. I can read. There are many common examples of pressure dropping in rapidly moving fluids. With the last sentence, this effect was observed as far back as mid 1800s when it was found trains passing in opposite direction to precarious toward one another. And then, like, I can't speed read. Don't do that. You should take your time reading through it. But at the same time, if a particular sentence doesn't make sense, ignore it and keep reading. And it might be that it's necessary for you to come back and read it a second time. And I'm advising you to ignore it and keep reading, because maybe as you keep reading, it makes sense to you eventually why they said this. You don't want to get stuck at a single point just because what might have been a minor misunderstanding or kind of not lack, but like less smaller degree of understanding than what we are hoping for. So I'm gonna keep going. There are many common examples of pressure dropping in rapidly moving fluids. For instance, shower curtain. Oh, I could speed read through this. These are a bunch of examples. Let me read through it. Have a disagreeable habit of bulging into the shower stall whenever the shower is on. The reason is that the high velocity stream of water and air creates a region of lower pressure inside the shower, whereas the pressure on the other side remains at the standard atmospheric pressure. This pressure difference results in a net force pushing the curtain inward. Similarly, when a car passes a truck on the highway, the two vehicles seem to pull toward each other. The reason is the same. The high velocity of the air between the car and the truck creates a region of lower pressure between the vehicles, and they are pushed together by greater pressure on the outside. Um, I guess that might be true. I'm trying to imagine this in the reference frame of these two cars. I guess it does look like there's a higher velocity. Maybe, I don't know. Fluid dynamic stuff. I will tell you that a lot of it is that, um, intuitively understandable to me. But they're saying this effect was observed. If it's experimentally observed, then yes, I trust that. Experiments, I do trust. Theoretical reasoning, maybe, maybe not. When it was found that trains passing in opposite directions are different from the same direction, though. So tip the precariously toward one another. Um, Maybe, I don't know. But so I'm again doing the thing that I described. Whether that effect, this situation they described is true or not, whether I understand it or not, I don't think it matters too much. So we'll keep reading. Energy conservation and Bernoulli's equation. The application of the principle of conservation of energy to frictionless laminar flow leads to a very useful relation between pressure and flow speed in a fluid. This relation is called Bernoulli's equation, named after I didn't know his first name. Daniel Bernoulli. Oh, there are, I think, a bunch of Bernoullis. So I'm not gonna get too stuck on Daniel, although I guess this is one of the Bernoullis, who published his studies on fluid motion in his book Hydrodynamica, 1738. Consider an incompressible fluid flowing through a pipe that has a varying diameter and height, as shown in the figure below. We'll look at that in a bit. Subscripts 1 and 2 in the figure denote two locations along the pipe
and illustrate the relationship between the areas of cross sections, A, the speed of flow, V, the height from ground, Y, and the pressure, P, at each point. So we have 1, 2, 3, 4 variables that's going to get subscripts because there are two different locations we'll be looking at. We assume here that the density at the 2 points is the same. Therefore, density is denoted by, this is not P. Look how different this letter looks from the P above. You should not be confusing these two. This is letter rho. It's a Greek letter that sounds like R. I usually write it with a single stroke, rho, without any subscripts. So density is constant throughout the fluid because we assume it's incompressible. And since the fluid is incompressible, the shaded volumes must be equal. Volumes of fluid, I think that's what they're talking about. Yeah, I think I see what their reasoning is. I think what they must be thinking of is if it's like air, like the geometric volumes being the same, okay, but they might be drawing the distinction between the volume of the fluid. If the fluid is compressible, then given the same quantity of fluid, its volume could change, maybe. Again, I think these nuances don't matter too much. Let me zoom out a little bit to show the whole thing. Yeah. So it's marking one position as subscript 1, another position as subscript 2, and all the dynamical quantities, they've given them a subscript to distinguish between quantities over here and the quantities over here. Okay, we also assume that there are no viscous forces in the fluid. Yeah, this is important part. So the energy of any part of the fluid will be conserved. It's important both for the derivation and for observation that Bernoulli's equation isn't always true. Like with the water, you can see significant differences, and that's because water does have viscous forces. To derive Bernoulli's equation, we first calculate the work that was done on the fluid. So they have this quantity they are labeling with dW. D means infinitesimal or very small amount. So very small amount of work done. They are saying that's the force on this fluid element, F times force, displacement dx1. So that's how much work you do on this if you push it for that distance. And they're subtracting. This is the situation that they are they have in mind in the rest of the derivation. So think of your portion of the fluid that's here. You can think of this fluid as kind of doing this movement over some infinitesimal amount of time or some amount of time. This fluid starts out containing this element here. After some infinitesimal amount of time, the whole fluid has moved. And the way it's moved can be characterized this way. This portion has come off, and this portion has been added. And now you might object, but what about this, the fluid that entered from here into here? That's not the same fluid that came out this end and into here, right? It's not the same fluid, but when we are considering the kind of the change of energy of this portion of the fluid, whether the fluid that came out at this end is the same fluid that came in at this end, doesn't matter. So we can do that switch rule without affecting any mathematical expressions. So in this first equation that they write down, so what they are looking at is for this element that moves in, there's going to be a positive work being done by this force as it moves this distance to enter this portion of the volume. That's been done, positive work. And as this portion out kind of squirts out on this end, this force is going to be doing negative work because it's pushing against the direction of motion. And with the negative work done, it's going to take out some energy, and that's why there's a minus sign there to indicate all that. So okay, that expression I think makes sense to me. And so when you look at mathematical equations, you've seen me done both. I think in the past sessions you've seen me basically skip over equations because it made my head hurt. Sometimes I do that. What I will tell you is that when it's a derivation and you are seeking to understand the derivation, you should do this exact thing I'm doing, which is taking enough time with each equation and making sure that you understand it before you move on to the next. So it looks like I'm doing different things at different times, and that's because, yes, I am. There's an element of judgment where, and I will tell you, if you're not sure, the easy thing to do by default is skim through it first, because the things that were mysterious, maybe the second time you see it, it'll be less mysterious. So like if you're not sure what to do, skim through it first. You can always come back later. That's the advantage of written material. So, okay, this equation makes sense. So I'm moving on to the second line, the infinitesimal amount of work. Okay, this looks similar to that. So I will bet they are expanding out F1. Yeah, F1 is that pressure times area. They've done that there. Yeah. And here F2 is pressure times area. Yeah, they've done that there. So they are taking this expression, cross-sectional area times the displacement, and express that as a volume element, dV. And as they are expressing volume element, they drop the subscript. Instead of saying dV1 and dV2, they've said dV because they've constructed the situation so that these two have the same amount of fluid. That's how I was describing. Some fluid comes in here, the same amount of fluid goes out here. So, okay, so the second equality makes sense. And now that they've gotten dV in the same form, they factored it out. So it's a pressure at one point here minus pressure at the other point here. Okay, let's keep going. So that line makes sense. dW is equal to difference in pressure times the volume element. It's quite elegant derivation, and I think that's the part that I keep messing up when I'm trying to do this on my own. The work done was due to the conservative force of gravity. Wait, what? Let me keep reading. Work done was due to the conservative force of gravity and the change in the kinetic energy of the fluid. All right, I'm gonna keep reading. The change in the kinetic energy of the fluid is equal to this. Okay, difference in kinetic energy for this infinitesimal amount of fluid is moving is 1/2. So they are taking the amount of mass here, which so they are doing the same thing they did when they were setting up the equation. So, so taking this amount of fluid that you start out with, they are imagining adding this amount. That's the part of the fluid that squirts out. So plus 1/2 m2 v2 squared minus, and they are imagining taking out this portion of the fluid, part that goes into this common shared portion. So minus 1/2 mass of this fluid times V1 squared. And because the density is constant and the volume is the same, these two masses are actually the same amount. So they factor it out as rho dV. So I think this expression for change of kinetic energy makes sense to me. The change in potential energy is, again, small amount of potential energy change, and they're doing the same thing here. There's a portion that squirts out. There's a potential energy here that's associated with that height. That's mgy2 minus. There's a potential energy associated with this amount. Subtract that since that's in the common shared part, mgy1, and express mass in terms of rho dV, and express G is same constant, and I guess if they were being consistent, this should have been M1 and M2, but it's fine. It's same quantity anyway. Sorry, M2 and M1. That's what it should have been, but again, it's fine. Doesn't matter here. Okay, so these two equations, I'm fine with the equations. And the energy equation then becomes, they say this, okay, that I agree with. The amount, infinitesimal amount of work done, that it's numerically equal to the infinitesimal change in kinetic energy and the infinitesimal change in potential energy. What I have an issue with, and that's the reason I was posing, is the kind of causality assigned here. Like work done was due to the conservative force. That's good. I don't have an issue with that. Change of kinetic energy doesn't cause the work to be done. It's the other way around. Work done causes the change of kinetic energy. But the nice thing about mathematical equations is that when you have equation doesn't care about causality. It's equal on both sides. You can reverse them. It's fine. so this equation is valid. No problem with that. Now that we have this, we can use the three pieces derived above. Plug in the expression for infinitesimal amount of work, expression for infinitesimal amount of change in kinetic energy, infinitesimal amount of change in potential energy. You see a lot of things that cancel out. dV, common volume element, cancels out. And I guess that's it. So the difference in pressure is equal to, and this is really the reason for introducing density in this context, because so if you just kept this as mass, that's like the simplest form it will remain. But by expressing mass as density times volume element, you can cancel out the volume element and have something in terms of a constant quantity. So when you rearrange this equation, that gives you the Bernoulli's equation, and and that's the derivation. You can think of, so this form of equation is nice because I hope this reminds you of the conservation law. So you have some quantities measured and tagged at some point that's equal to the same combination of quantities: pressure, this kinetic energy related quantity, this potential energy related quantity, tagged and measured at another location. And it's showing some sort of form of conservation, and that's because it comes from conservation of energy. So yeah, that's the derivation, and I think this is definitely shorter than my other longer meandering lectures. So I'll replace that one with this, and yeah. So the relation states and all that, and you can read it through the rest. Special note must be made here. Pressures at the same height in different parts of the fluid may be different, if they have different speeds of flow. So like here, you can imagine the y1 being equal to y2. But if the diameter of if the size of the tube is different, then speed will change, and that will cause the pressure to change. And they have some examples which I encourage you to look through. I won't right now because I want to do the other thing. Entrainment, that's fun. You might have seen a demo of. So I believe there are two practical things. There's like a Dyson fanless. Wait, there might not be entrainment, but there's like a fanless, bladeless fans. I think they use some sort of fluid dynamics phenomenon. I don't know if they call it entrainment. It might be, not sure. and they give you other examples too. So you just let that be. I think.